Welcome to Complex Analysis. Today, we are going to explore one of the most fascinating and powerful concepts in mathematics: residues. We will learn what happens when a function breaks down and how the leftover mathematical footprint can help us solve seemingly impossible problems. By the end of this video, you will understand exactly what a residue is and how to calculate it. To begin our journey, imagine walking around a park. If the park is completely flat, walking in a full circle brings you back to your starting elevation with zero net change. In complex analysis, integrating a smooth, well-behaved function around a closed loop is just like that. It always gives a result of zero. But what if there is a massive, bottomless fountain in the middle of the park? The path is fundamentally different. The hole exerts a mathematical gravitational pull. The leftover footprint, or the toll you pay for walking around that hole, is what we call a residue. Now that we have a feel for what a residue is, let us define it formally. In complex analysis, an isolated singular point is a specific spot where a function becomes undefined or shoots off to infinity, even though it is perfectly well behaved everywhere around it. To understand the function near this point, we use a Laurent series. Think of it as a Taylor series, but it includes negative powers to account for the singularity blowing up. The residue is defined specifically as the coefficient of the 1 over z minus z0 term in this series. This brings us to the mathematical form of the concept. Here we see the Laurent series expansion. The function f of z is expanded around the singular point z0. The negative powers represent the principal part of the series, which is exactly what causes the function to blow up to infinity. Among all these terms, we are looking for just one specific constant, a minus 1. This coefficient attached to the power of negative 1 is the residue. If the singularity gets stronger, the negative power terms dominate more, but a minus 1 remains the unique weight of that specific pole. Before we move on, let us see this with a concrete example. We want to find the residue of the function e to the power of z divided by z cubed at the singular point z equals 0. The function blows up here because dividing by 0 is undefined. To find the residue, we start by writing out the known Maclaurin series for the exponential function in the numerator. Remember, the exclamation marks are factorials. We then substitute this infinite series back into our original function, keeping the 1 over z cubed term on the outside for now. Continuing with our calculation, our next step is to combine the outside term with the series. We distribute the 1 over z cubed across every single term inside the parenthesis. By multiplying the terms through and simplifying the fractions, we successfully generate the Laurent series for our function around the point z equals 0. Notice how the positive powers from the exponential function have been shifted downwards into negative powers by the denominator. This shift is exactly what creates the principal part of our series. Now we just need to locate our residue. By definition, the residue is strictly the coefficient attached to the 1 over z term in this new series. Carefully scanning our simplified series, we find the term 1 over 2z. We can rewrite this as 1 half times 1 over z to clearly separate the coefficient from the variable. Therefore, the coefficient we are looking for is exactly 1 half. This means the residue of this function at z equals 0 is 1 half. Physically, this is the mathematical weight of this specific singularity. Now that we have used this series approach, let us understand where the true power of the residue comes from by looking at its contour integral. We want to integrate our function along a closed circular path, C, that surrounds our singularity. To do this, we substitute the entire Laurent series into the integral. Because integration is a linear operation, we can bring the integral sign inside the infinite sum. This means we just need to integrate each individual term of the series one by one. This setup is the crucial first step in proving why the residue is so mathematically significant. Here is where a beautiful result in complex calculus appears. For any integer power n that is not equal to -1, the integral around a closed loop is exactly 0. This happens because those specific terms have standard, well-behaved antiderivatives. The starting and ending values of their antiderivatives cancel out perfectly. However, the term where n equals -1 behaves completely differently. Its antiderivative is a complex logarithm. When you go around the origin exactly once, the imaginary part of this logarithm increases by 2 pi I. It leaves a permanent leftover value that does not vanish. Because every other term in the infinite series integrates to 0, the entire massive integral collapses down to just one surviving piece. The coefficient a-1 is the only part of the function that survives the journey around the loop, getting multiplied by the 2 pi I that came from the logarithm. By simply rearranging this equation, we arrive at the formal mathematical definition of the residue. This proves that the residue is exactly equal to the contour integral divided by 2 pi I. This single surviving term is the core reason why residues are so incredibly important. Let us visualize what we just proved. Here we see the complex plane with the real and imaginary axes. The red cross marks our singularity, Z0, the hole in our mathematical park. The blue circle is our contour path, C, wrapping counterclockwise around the singularity. The integral along this blue path doesn't evaluate to 0 because the singularity is trapped inside. Instead, the path captures the residue, a-1, which represents the fundamental weight or strength of this isolated pole. So, we have proven that the residue connects to the integral. But writing out a full Laurent series every time can be tedious and sometimes very difficult. Fortunately, there is a better way for a specific type of singularity called a simple pole. A simple pole occurs when the problematic term in the denominator has an exponent of exactly 1. For these cases, we can bypass the infinite series entirely and use a clever shortcut limit formula to find the residue directly. This formula we just mentioned is the standard limit formula for a simple pole. Here it is written for a singularity at z equals I. Conceptually, by multiplying the entire function by z minus I, we are artificially removing the exact piece that causes the division by 0. Once that problematic piece is cancelled out, the function becomes continuous at that point. We can then safely take the limit as z approaches I to find the leftover value, which is our residue. If the singularity were at a different point, we would simply adjust the limit and the multiplying factor accordingly. Let us apply this shortcut to a new problem. We want to find the residue of the function 1 over z squared plus 1, specifically at the singular point z equals I. We first need to factor the denominator to clearly see where the function breaks down. Using the rules of complex numbers, z squared plus 1 factors into z minus I times z plus I. We then substitute a fully factored function into the limit formula. Notice how we multiply the whole thing by z minus I to target the specific pole we are interested in. This step reveals why the limit formula is such a clever trick. We now have a z minus I term in the numerator and a matching term in the denominator. These two terms perfectly cancel each other out. After cancelling, we are left with a much simpler, well-behaved expression. The division by 0 threat has been completely eliminated. Because the function is now safe, we evaluate the limit by directly substituting z equals I into the remaining expression, giving us 1 over 2i. We are almost done, but it is standard mathematical practice to move the imaginary unit out of the denominator. We achieve this by multiplying both the top and bottom of the fraction by I. Remembering the fundamental rule that I squared equals -1, the denominator becomes -2. This gives us a final calculated residue of -I over 2. This single complex number perfectly captures the mathematical weight of the singularity at z equals I, found entirely without integration. You might be wondering, why do we spend so much time finding these residues? In the real world, engineers and physicists constantly need to evaluate incredibly complex integrals. In electrical engineering, analyzing signal frequencies requires integrating over complex planes. In quantum mechanics, calculating particle scattering involves integrals impossible to solve with standard calculus. Residues provide a magical shortcut. Instead of performing grueling integration, you just locate the holes, calculate the simple algebraic residue at each hole, and add them up. Let us summarize what we have learned. A residue is the unique leftover value that remains when you integrate a function around a singular point. Formally, it is the coefficient of the 1 over z minus z naught term in a Laurent series expansion. By mastering how to find residues, whether through expanding a series or using shortcut limit formulas, you unlock the ability to bypass complex integration entirely. You have now seen how this concept acts as the ultimate bridge between algebra and advanced calculus.